Hey, my name's Dale, and I'm an applied AI engineer at Google. And one of the things that I'm most excited about in machine learning is natural language processing. Because over the past few years, computers have gotten really good at understanding language and even generating some of their own. So next month, I'm having a live Twitch stream with Scott Penberthy. He's the director of applied AI at Google, and also Chris Mattmann. He's the chief technology and innovation officer at NASA's Jet Propulsion Laboratory. And we're going to talk about some cutting edge techniques in NLP. But I've asked them what they're most excited about in this field to give you a little sneak peek.
Yeah, so what is the most fascinating thing happening in NLP these days? For at least for me, what to me is really sort of an eye opener is what I like to call Sutton's Law. And it's by Rich Sutton, who started and did a lot of work in reinforcement learning. And essentially, to paraphrase a posting he made called The Bittersweet Lesson, was that the ML that works is that scales with compute. And we're now starting to see tremendous advancements in the application of this model called a transformer from a few years ago. And Chris and I were playing with it with Bert. And that's so passe now. That's a whole year ago. But now what's happening is that model, much like CNNs were used for vision, when applied to a much broader space, a broader context, and a massive number of bidders, is now starting to do extraordinary things. Um, Bert gave us a hint. We've had derivatives of that at Google. We're seeing things like OpenAI and what to do in GPT-3. I think we're just now starting to see an era where these large scale models on top of a large scale of compute are going to allow us to bootstrap all kinds of sophisticated one shot learning. And as a bootstrap for a new platform for the entire industry, thinking about how do we model language in computers. So, that for me, Sutton's Law is perhaps the most interesting thing I've seen in NLP in years.
Oh, this is a tough one. What's exciting for me with natural language processing right now? I mean, for me, at least, besides the work that I'm doing with Scott, that we're going to have a great conversation with Dale and everyone about. So watch our coming Twitch stream on this, led by Manning. Besides all that, with Bert, by an encoder sort of encoder decoder representation of language, using 768 neurons. So in a compact representation, we can know what text corpora are similar, so that we could search it back or cluster it. We could look at basically that representation of relationships between words, and not only find things that are similar, but using very, very deep sort of semantic relationships. But additionally, these could be generator, used types of things. So you take a BERT representation and, you generate new texts and so forth for it, and sort of a GAN type of approach. So everything that's going on with adversarial networks and GANs, generative serial networks, everything that's going on with text on a similarity and an extraction and a search and a relationship type of area, those are things that are getting me really excited right now. Another thing I got to touch on is I'm an old school parser content extraction type of guy, and I've spent a decade or more basically writing parsers, making it so that you have to understand file formats and language. So the application of machine learning and deep learning to automatically extracting content from multimedia, from images, from video and audio, to recognizing kind of who's in them, running models like, Inception based on ImageNet, or the ease with which you can run a VGG model to get text out of, images and video and things like that. Those are things that excite me because I think they're really untapped in the content extraction space, and people still do it in sort of an ad hoc way. The last thing I'll add that's just, I think, really fascinating to me too is basically neural machine translation. So the ability to line up parallel corpora to basically go from Spanish to English automatically, or any to English, even using low resource languages where we don't have a lot of sort of automatic parallel corpora, and maybe we only have 6,000 parallel sentences or things like that. The ability of machine learning neural networks now to line up and learn the nuance basically between understanding language and machine translation automatically. I'm one of the people that still has the old statistical machine translation yellow book, and it's like black magic and dark arts to me. So, Neural MT, the TensorFlow 2 example for Spanish to English that's on the website right now, that's really exciting for me. So those are all the things that I'm really excited about, for NLP. So thanks for asking that question.
Hey y'all, I'm Dale from Google, and I'm joined by Scott, also from Google, and Chris from NASA's JPL. Hey guys.
Hey, good morning.
Morning. So let's see, last week I think I asked you what you were most excited about in natural language processing, and you gave me some awesome responses that gave me a lot to think about. And one of the things that I thought was very interesting was something that you said, Scott, which is what's fascinating to you is algorithms that scale with compute, because the idea is if you just add a lot more data, a lot more computational power, if it scales, then your model gets a lot more sophisticated. I think we saw a really good example of this in June when OpenAI released GPT-3. It was sort of all over the news that it was this model that could do things. I think it blew a lot of our minds. This huge text model could write poetry, it could write code, it could do translation, all these things that it wasn't even designed to do, it was just really good at. And I think that's really made people's mind explode with all of the possibilities. I mean, Chris, you listed a bunch of different problems, extraction, search, all these different things that maybe a model like this could really help with. So I wanted to start this talk by jumping into the technology behind these models. How do they actually work?
Oh, wow. So we have a couple hours to go through this, right, Dale? So so you got your whiteboard, Chris. We'll kind of go through. Yeah, exactly. He's like, no, we'll turn you off. No, I think it's the whole thing is how do you represent words and language, inside a computer? And so we all grew up and we all learned parse trees. And I think, Chris was smiling in his preamble. There's the noun, there's the verb, and you create these trees. But there's a shift around 2015 where they said, can we have a more concise, denser representation? Because you can take all the knowledge of what a word means and embed it in a vector, right? So how do you take the knowledge of what a word means, like the word bank? You can bank your car around the edge. When you drive fast, there's a river bank, there's a little bank you go to draw out money. Same 4 letters, bank, but has different meanings. So how do you encode all that and embed it in a vector? And there was a neat exercise called Word to Vec around 2015. And that was pretty neat. So what they did is they took what's called a one-hot encoding. So you have a vocabulary of 30,000 words. And you line up a 1 for that one word. And so you have a vector of a lot of zeros and a 1. And you squeeze it through a narrow neural network, and you try to guess the next word coming out. And so you get these networks that sort of shape like an hourglass, right? And you take 30,000, you squeeze it through 100, and then you guess the next word. If you do this enough, that actually works. And so it's cool. So you take the 30,000 and you embed the word, what that word means, into 100. That's kind of how it started.
So it sounds like what you're describing is one of the major changes in the way that we build these types of models is that we have better ways of representing words. Words as vectors, where vectors are points in space. Exactly.
And then, so what was really curious about that in 2015 is that if you were to take that vector, the 100-dimensional vector, and even project it onto 2D, right, through, do a projection at 2D so you could plot these, or 3D, they started to have Euclidean properties, which was sort of freaky, right? So you had, you had queen and mother and female all and you can actually do a transformation and have that say male, king, and father. And they're like, that was kind of cool, right? And so you started to see these relationships where they had Euclidean properties, and you could now manipulate words like vectors. And I think then, I think Chris and I started to talk around me, Chris, and then you got interested in this as well, right?
Yeah, the trick for me, is how different the process for doing this is today than, it sort of used to be. We spent so much time basically doing, like Scott was talking about, statistical models. That's kind of where I came up before I learned this, these dark arts and Horcruxes and, all the stuff that we're talking about here and deep learning. And basically it's language modeling. And we did so much effort to basically take corpora and then pull in whether it's a noun or a verb, or the relationships between language, whether it's a noun or a verb. And we did all this labeling. And basically the difference now is that you don't need to do that today. You infer the relationship, basically you learn the features. And that's the benefit of these sort of black boxes, these neural networks, is that the feature engineering is all sort of automatic as opposed to sort of statistically generated before. And Scott and I tell you this too, Dale, is I'm just sitting here, it's it's like, oh, we're supposed to be the leaders in some of these, domains, and I'm just sitting here in awe, you know, poor little boy here coming from a trailer, wow, I learned statistics and thought I was smart, and then now it's all doing it by itself. So.
Well, then I guess if you're somebody watching, then you're in a good spot because you're on the cutting edge of NASA and JPL. So that's kind of cool.
Yeah, there you go.
So what I'm hearing from you, Chris, is that what's something that's different about these models today than the statistical models that you're used to building. I'm kind of hearing two things. So it sounds like the first thing is that, and I know this is true across a lot of types of modeling problems, is that it used to be that human beings had to do a lot more work to sort of set up these problems. They had to label nouns and words, and they had to do a lot of work beforehand before building a model. So does that part sound right to you?
Yeah, and most of that work was driven by sort of domain specificity and a high cost per label. One of the big things in machine learning nowadays, one of kind of like the future, things that people are working on is learning with less labels. Like how can we reduce the cost? How can we make everything like labeling a cat video? And it's the same for text. It's like, how do we not have to have this big domain specific where you need a PhD in that domain, manual laborious effort to collect, curate the labels for structure? And how do we just, Scott's favorite thing, how do we represent like the brain or the eardrum or, our, basically visual cortex, and cornea and things like that? How does biology inspire us to do it? And so it's a different way of model building, and it's actually at a much less cost on the labeling and the feature engineering part. And so that's really important for me. The more that we make basically machine learning require less labels without trading accuracy and all that, and it applies to text too, that's super powerful. Those are game-changing techniques.
This is a really relevant comment you're making, because somebody here in the chat says, well, in specific domains, trust me that you still need to label for syntax and semantics. So this problem of, oh, well, you can build something that understands general words, but how do you also do the same technique for a domain-specific thing? I think still a hard problem.
Yeah, I think, well, it's a very hot topic. I think, there's from 23 years ago, there was a neural network technique called an LSTM that was created, right? And way ahead of their time. And they had the way to sort of understand, how words change based on how they're used. Like we talked about bank before. If you look at how I use it in the sentence, the meaning shifts. And they built a neural network, basically a component that allows you to do that. But the problem with LSTMs is they're hard to do transfer learning. In other words, once you train it on one set of languages, it didn't transfer very well. And there was this breakthrough in 2017, which was sort of an evolution of word to vec, and people started to add this notion of attention, paying attention around you, and they generalized it. And what's interesting about that is they generalized it and they mapped the math to take advantage of GPUs in parallel processing. So if you were to do this by hand, you'd be like, my God, it's a lot of calculations, right? The LSTM is so much more elegant. If you look at actually the transformer, this model basically used high dimensional, basically parallel processing and really fascinating models to look around the context. And this now you can actually do transfer learning on. And so what that means is you can actually have a model that's generic on train, like a GPT-3 or a BERT. And what you see in the chat, you can now take that, and we're seeing it, and learn domain specific ones. So in the industry, you'll see this is like AutoML is the current name for this, right? And the idea is you can take a generic model and then train it on a language for your domain, and you can own that piece. And that is really starting to capture the imagination of a lot of people. Because back to what you said, Chris, is that labeling everything else. If you have a model that can transfer learn on a smaller domain in just a few examples, that's astounding. Right. And I think that's really sort of catched imagination. And now it's sort of a running up the bat in terms of who can do it fastest. Right.
So you mentioned a couple of things here. So first of all, this idea of the transformer, so versus the LSTM. So the transformer is, like you said, it's this new type of architecture for neural network. It's the architecture behind GPT-3. And one of the things that you pointed out that's so unique about it is that it's easier to train computationally and do transfer learning on. Is that right?
Yep. I think it's really designed really well, such that the computations you do in a transformer map extraordinarily well to a GPU, right? And so these new devices. And so if you take an LSTM, it's elegant mathematics, and people have tried to beat it for years, but it's so elegant, but it doesn't really work well on a GPU because you're going between main memory and GPU, and you're shuttling back and forth. And they said, can we optimize this somehow? And so now you've got this mathematics. It's all about attention. There's a great paper called "Attention is All You Need," and it's a little provocative. But the idea is that you pay attention to the context in which your language is being used, and then you look at what you're trying to generate, and you can play off those two contexts to figure out the next thing to generate. And that is,
I want to go into that because this is a very interesting topic. So one of the things that I think is what is so interesting about these new models is that they learn a lot, a ton. Most of what they learn comes from unlabeled data. That's a huge deal because we have way more unlabeled text. All of the internet, all of Wikipedia is unlabeled text than we have labeled text. So can you talk a bit about how models learn from unlabeled text data, like for example, the corpus of all Wikipedia articles?
Yeah, I mean,
go ahead, Chris.
I was going to say, I'm going to throw in here from I shouldn't be the guy answering this question. I'm supposed to be the space cadet, but I'll kind of tee Scott up, here or whatever. So I shouldn't be talking about this next thing I'm going to talk about.
You are the author of the new upcoming TensorFlow 2 book, so I think that your expertise goes beyond just space.
Hey, let me figure out which way to point. All right, thank you, Dale. I appreciate that, and thanks for throwing the book out there. But yeah, so I got really into Spanish to English due to some work I was doing with the Defense Department and doing translation. For that, the amount of work that we had to do. I mean, I used to carry around Philippe Cohn's yellow book, the big StatMT book. Forever. It was the Bible. You read the different steps in that book to basically train up a statistical machine learning model. You got to know all about the language rules, the grammar. You got to basically do parallel alignment of corpora, all of these steps, And so basically today, what happens? You need really parallel corpora, parallel sentences and things, but you don't need to know the grammar, the language, and the whatever, because really the design of these network architectures are basically set up to learn those things. And I'm gonna grab this baseball up here and throw it down, to Scott. But that's the basis for what he's about to explain.
So what you're describing is a pretty common trend in deep learning with really big data. It's actually kind of what we just talked about. How you don't need to specify as much information up front. How does the language work? What are the nouns? What are the relationships? Because the models can actually learn those things themselves.
100%. Right. Yeah, we call it Mad Libs. Go on, Mad Libs, Scott.
Mad Libs, that's Bert, right? Yeah, I think what's an observation is that our face, human language, regardless, and how humans communicate, they form a probability distribution. The eyes tend to be right next to each other, and there's a mouth, then there's a nose, and there's a mouth typically, and they have different sort of shapes. There's a distribution of faces. That's a probability distribution. Right. Same thing for human language, and how verbs and nouns and whatnot, that forms a distribution for a particular language. And now you're creating these networks that can learn that distribution, and not only learn it, if you give it a sample, it can generate stuff from the distribution. Right.
So take me from the face example to the text example. I need the bridge there.
Okay. All right. So think of, in English, the way we express ourselves and the way this language forms a statistical probability distribution. Right. In other words, if you say a verb, most likely you're going to say, an object of the verb next. Right. Or if you have, and so the idea is that instead of having to frame this, there's a pattern to how these sentences form. And there's lots of different patterns. And so when you have sufficient examples, you can start to detect these patterns statistically. And what's interesting about the transformer model is it sort of generalized a technique that's been going on for a few years, where it started with word to vec. That the idea is take a word, squeeze it through a network, and get a vector for it. And they said, well, you need to know more context, and they started to look at what's the words around it, right? So that the next thing word to vec is don't just do the next word, do the word before and after. That's trigram. And then Bert came along and said, no, that's what Chris said. Let's play Mad Libs. So Mad Libs was, let's sort of we'd use this model, and what we're going to do is we're going to take a paragraph, and I'm going to knock out 5 words. You guess them, right? And if you look at enough paragraphs on Wikipedia, turns out the network starts to learn what the meaning of these words are, the context around it. And that was about 100 million parameters using this new architecture called a transformer. And what the transformer did is allows you to pay attention to the words before and after the words you're trying to understand, or the sentences before and after. Right. So someone took Bert and said, wait a second, instead of words, how about whole sentences? So Pegasus was like, let me guess the topical sentence from a paragraph. And now now you have the ability to summarize a paragraph by guessing the missing sentence.
So what Scott's talking about here, by the way, is GPT-3 is the new hotness, but it really started with BERT, which was 2015, I think. Right.
Yeah,
and then there are all these models.
2015. Yeah, and the
Oh,
transformer came, and then they did
and
bidirectional
then we're
encoding.
making all of these
Yeah,
improvements. And it seems
exactly.
like the improvements, in addition to the architecture, a lot of it's coming from the training task. How are we taking the data and what are we asking the model to learn to do?
Yeah.
Yeah,
And so
that proves it's not just smoke and mirrors too. By the way, every one of us has our aha moment, and we cling to that moment like nothing else. So it's like, like I was telling you, Dale, when we were talking before, it's like for me, 2014, what I was doing these DARPA Memex things, nothing will ever change. Everything will be relatable back to that. So for Scott, it's going to be all relatable to Bert, and it makes sense because it is, and it's true because we said it on this Twitch stream. But that's everything. We have our aha relatable moment, and so it all goes back to 2015 on this. So
I actually have my own Bert. Sorry, I didn't mean to cut you off, but I have my own Bert moment as well because I started in Google Research the year that Bert was released, and I just remember it being so interesting. I was building an LSTM, which you talked about, which was the
there you go. Yeah,
things,
they're
right?
awesome.
And
they still are.
and then the Bert paper came out, and everybody in my research was like, "Well, can we try this on Bert?" And then everybody else and everywhere else in Google Research was like, "Oh, can we do this on Bert?" And then Google Search was like, "Can we do this on Bert?" So it really kind of spread like wildfire, at least throughout Google.
Yeah, and I think if you look at the transformer was designed, the mathematics to work in parallel processing, because you could parallelize and look at a lot of the words in parallel and try to figure out the weights of how much do you pay attention for each different layer of the network to the previous word, and you could build all kinds of attentional models inside the network in parallel. So that was super cool. But then, Rich Sutton, we talked about before, had this idea or claim that maybe it's an observation really, is that the models that seem to be working best are those that are really taking advantage of compute. And so why not do something extraordinarily large? So to go from 100 million to 100 billion parameters, 175 billion. And on the path to 175 billion, it's very data hungry, but now you can look at different patterns in like an entire Wikipedia. And now we're finding those very, very large models are doing extraordinary things, right? Because these models, I guess transformer was the first thing that could actually scale to that scale. Right, you don't get vanishing gradients, exploding gradients, because now you've got these rich attention networks. You can look at broad corpus. So instead of looking at, the baby was like word defect, the next word. Now you're looking at entire, hundreds of words or maybe an entire document and getting the context from that. And that is just so powerful. And I think we're just beginning to, this is just the third version. And now, right, I think we came out with a reformer. Oh, look, we can do it faster. Yeah, so I think the industry's now latching on and saying, how far can we take this, right? What else can we use in this model where by leveraging compute, what happens when you have an extremely large model?
My neural network is telling me that all of these components that we're building must be named ER at the end. It told me to pay attention to that.
ER at the end?
Yep.
I think your training sample's too small.
Yeah, exactly.
So I have a great question from the chat here about these types of models. But first, I just want to quickly summarize. So if we had to say like two bullet points that people take to understand, well, what is this new type of model that's been changing NLP? I'm going to say, based on what you guys said, it's this way of using unlabeled data for training, and this architecture that happens to scale really well with compute, happens to be really efficient. And these two things combined lead to these models that are much larger than anything that we had to contend with before. Would you guys agree with that?
That's what you do so well, Dale. I love it. I think you nailed it, right?
I'm like an encoder, right? Like
well, it's GPT-4, Dale Markowitz,
Right, there she goes. She's not
All right,
actually
let's
real.
go into the chat question. This is a question that I'm interested in. It says, It seems to me that the main benefit of GPT-3 is memorization capacity due to the size of the training set, which is enormous. I think it's like the whole common crawl. It's a really large data set that this model's trained on. So the person says, it's nothing more than that. Do you share this point of view?
Depends what you think you're memorizing. If you think it's memorizing facts and it's spitting them that out, I don't see it doing that, right? And it's more what it's seeing is it's learning, and it's encoding in those large networks many nuanced relationships between distributions, right? And it's learning, and those different relationships at scale allow it to do things that sort of leave me awestruck, at least. Right.
Yeah.
Because it's funny, nuances in our language and nuances in how we summarize and nuances in large corpora that we as humans have a hard time expressing statistically, but it's funny.
Yeah.
I don't know. What do you think, Chris?
I want to back Scott up on that. And so for me, it's the generative aspects of it that tell me that it doesn't just do memorization. If you look at technologies like Grover, or if you look at, tech that's very similar, which basically has the generative component of this to generate, say, new, well, I won't say facts, but new, you have pseudo facts or things like that, either articles or, papers or, things like that. It's the generative notions for it that tell me that it didn't memorize those because those didn't exist yet. So it learned the relationships, and so forth between them.
Can you elaborate on that? What do you mean the generative aspect?
Well, the fact that, again, going back to things like Mad Libs and things like that, but it learns, like, if I want to write, I'm going to ingest a bunch of, I don't know, I'm going to ingest a bunch of Bible chapters, into it, like Scott and I did in our second blog post and things like that into things like BERT. So it learns the relationships. But let's even, think something very similar. The next steps, like you said, GPT-3. And then from that, I can generate, say, new Bible chapters or Bible verses or things like that didn't exist before. And what it did is it learned that, Bible chapters in the Old, Testament or whatever talked a lot about goat's blood and, putting stuff on doors and, things like commandments and things like that. And not just the words, but the fact that when they co-occurred with things like walking up a mountain or with, three men or this and that when it generates the news story or whatever that have elements of this, with things switched out across that probability distribution that Scott was talking about across those relationships. That's what I'm talking about. It doesn't just
learning those functions, right?
It's learning those functions. Yeah.
Right. So think of like the first example we talked about is Euclidean distance, right? So these projections in 3D space seem to work. So, historically, man to king, woman to queen, and you can actually do transformations and take 2 points in space, man and woman, and project it, and it says, man is to king as woman is to queen. You're like, that's amazing, but it looks like just a projection in 3D. So now with these things like GPT-3 and BERT, you can say the population of Boston and San Francisco and put the number down. And then you put down New York City and it auto completes the population in New York City. Like, did it memorize that? Well, no, there's a high dimensional relationship between our notion of that number and this city that it's figured out. And it says, if that's a projection from Boston to this number and from Seattle to this number, then the projection from New York to this must be this number.
Yeah,
it's very very interesting.
I call that formalizing the feels. So in the book a little, I got dad jokes. Scott wrote the foreword to my book, or whatever, and God bless him. And there's a lot of dad jokes in there, and one of the dad jokes is talking about the feels, and the feels are you ever like think of things that you kind of complete for another friend or your family or your mom or your dad. You complete a sentence for them, or you just it's kind of like what Scott was just talking about. It's like it's the feels. Believe it or not, there's a foundation for that, for the feels,
right.
For completing that.
So let me make sure I understand. So the feels are like, it's kind of like this this style that's hard to put in words. Is that what you're describing?
Yeah, the parts where someone is like you said, Scott just talked about, guessing the population of something or, whatever, or having the model do that, or, with mom and dad, mom wants chicken tonight, for dinner or whatever. And you kind of just felt that, well, and why? Are you clairvoyant? Are you an ESP, or is it because over time, in this certain relationship, or when it's actually kind of, semi-sunny outside, or when you have a bunch of basil in the house, mom wanted chicken. And you don't know why, but the feels were kind of,
right.
But you figure it out, and so what these are, they're foundations or formalizing for the feels, and things like that.
Yeah, I think this is a really, when people are like, well, what's with this whole machine learning thing? Why is it important? I think one of the things that really stands out to me is that there's this whole set of things that we know that we just can't put into words, which sounds what you're describing with the fields. And computers this is a way that they can finally do that, even though we can't tell them how. One example from GPT-3 I saw, which I thought maybe is pretty compelling, is I saw some examples where people could use this model to get the model to write like a limerick or write this in the style of this author.
Sure.
And I think, if that was your example of why this model isn't memorizing things, like there's definitely no example of, a limerick about Elon Musk until this model came up with it.
Yeah, so it's neat. So if you look inside GPT-3, you're not going to see, much like look inside of a brain, you're not going to see limericks stored in a directory somewhere, right? Instead, what you'll see is like, if you'll see these relationships where if you start to utter the words of a limerick, right, statistically, there's a pattern in that, right? And as a result, I can generate words that statistically follow. If I've seen it, millions and millions of times, I start to get a sense of what comes next. And I think we saw a version of this in images with faces before GPT-3. I think NVIDIA did that, right? And it kind of started
about generating really realistic human faces that are
right. So how's
new.
that happening? We think that, but there's something about nature is that we expect the eyes and the nose and the mouth to be somewhere, and all the way down to the pixels have distributions. So if I can kind of sketch, it can sort of fill out saying, after seeing millions of human faces, these pixels statistically show up. Like, that's amazing, right?
That's right. Have you ever dreamed before that you spoke in a language that didn't exist? So like for me, like GANs and generative stuff are the dream world, right? Either you're imagining faces of people that are combinations of ones of things that you've seen that maybe don't exist or that you haven't met. The same thing is true with language. Have you ever, remembered having conversations in your dreams that you never had before, or that
like even Sims language or something?
Exactly, or speak,
yeah.
spoken different things. In my mind, that's your mind going full GPT-3, or whatever, and generative, so.
The essence of language, yeah. Another good example I've seen image models that generate like pictures of dogs, but these earlier dogs where it's like from far away, you're like, yeah, a bunch of pictures of dogs. And you look and you're like, that has 3 legs and like, what is that thing? It just has the essence, but it's not quite a dog.
100%, exactly. And I'm glad you brought that one up. DC GAN is my favorite example for that, and there's even some TensorFlow. There was a big Kaggle competition on that. I've even got a notebook in my GitHub if anyone in the audience or wants to look. I jacked it from someone else and modified it, but I love it. It generates scary dogs for my kids, and they're like, "What the hell is that?" And my wife's like,
right?
"Oh my god!" But then at the end, it looks like Fido, and it's great.
Yeah, so I think if what's interesting about the math, inside a transformer is these techniques are such that it's so fine grained that we don't yet know how far we can push it. Right. And it has a lot of promise. But I think, if you look at the encoding a language, that's sort of a sequence of values. Right. And they actually use something called byte pairs. Because if you look at, different languages have different sort of byte pairs that show up because, the characters are different. And so now you think about, well, what's 10 times larger than GPT-3? Right. And now you're starting to track, like very large scale AI, you're starting to track in an order of trillions of connections. The human brain's 100 trillion-ish. Right, connections, and so the BERT model, was only 100 million, right. Now we're getting to 0.175 billion. So what happens when you get a trillion? What happens when you get to a trillion connections? What's that going to do?
This is a really great transition into another question that was asked in the chat, which is about the energy footprint of GPT-3. There's a tendency to take into account energy footprint attached to really huge language models. Can we imagine that? Is it worth the price? And I want to add to this question, not just specifically about the energy, but if these models are so big and they require so much data to train, so much compute, how do you imagine Google can do it, OpenAI can do it, but how do you imagine developers at smaller companies working with this type of technology?
I have a couple of thoughts there. I think it's maybe a provocative statement. I think that these large models may be more energy efficient than the way we do things today. And the reason is that because these models allow you to take a distribution and then tune it, so it's called transfer learning, to your own particular model. The notion is you could have a few places that you generate a starter kit, right? It's like the sourdough starter. But you can, once you have that, right, monetizing that and using it, you just add a little bit of energy on top of that, and then create an entire model that you don't have to recreate. Because today, if you look at AI research, it's like create a new model, get your, run it for several weeks, get your PhD, right? And it's like, why are we doing this, right? We're all starting from scratch. And what about very, very large models? And instead of having multiple different models, we as humans can go between language and vision and speech, and we have that benefit. Today, it's like, no, there's this ASR community, then there's the self-driving community, and then the language community. A lot of similarity, but how do you build something that large so we can share and be much more energy efficient? Because the brain's like 25 watts. If you really think hard and get a headache, that's 25 watts, right? So why can't we build models that large? And I think once we figure that out, the ability to use them may be far more energy efficient than having thousands of different companies building their own models.
Yeah, my big foray into this was with computer vision when we were looking at Mars images and then trying to figure out how to automatically caption them and label them. We looked into creating our own model, but then quickly were found things like show and tell from Google and things, and show and tell with attention.
All right, Chris, I'm going to stop you right there because we need to talk about that. We can't just have it as a side note. Okay. So let's talk about some of the coolest use cases that we see from these language models. One of the ones that came to mind that really blew my mind was this project using models like this to generate text to describe pictures of Mars. Please give us the full details on that.
Cool. Yeah. Well, I knew Dale was excited about this or whatever, because, we talked a little bit about this, and I am. I mean, it's one of those like, belly button things that, I'll probably never do anything at NASA or JPL again, but I can always point back to this, or whatever. This is one of my things. It's so, okay, a couple things. So between Earth and Mars, it takes 8 minutes to send a communication there and to get something back. We call it, well, I'm going to mess this up, but we call it the 7 minutes of terror because it's somewhere between 7 and 8, but I round it up. But, and so basically during that time, during critical events, like if it's entry, descent, and landing of one of our big rovers on another planet, it's 7 minutes of terror because we're hoping that the EDL worked and that we got the messages back and it didn't crash. And so far, by the way, the U.S. has been, the only nation to land something on another planet, which is, on Mars, to land a lander there and a rover there and to have it be successful. And, related to so we're pretty good at it, and so that's great. So that time lapse creates a very thin pipe between Earth and Mars. And so we have to use that bandwidth efficiently. Also today on rovers, they're running things like the iPhone 1 processor, which we call the RAD 750. Why is it running an iPhone 1 processor? Because we need our stuff that goes up into space and lands on other planets to be resilient to what we call cosmic radiation. That's basically radiation that does wiggy stuff to the hardware. It like flips the bits.
Whenever I have a bug, I'm like, yeah, it must be the cosmic radiation.
It must be the cosmic radiation. It's the cause of a lot of things. It's the cause of a lot of things. It becomes shortwave radiation and then other radiation when it gets to Earth. But anyways, we don't care about that. We're talking about other planets. So, the cosmic radiation flips the bits. And so because of that, we need older technology that is what we call radiation hardened. And so that limits our ability to do all the cool stuff that Dale and Scott do at their amazing Google company and that other companies do. So we don't have big GPUs in space yet, but tomorrow we will. And when we do, when we have high-performance space-flight computing, and when we have things like the Snapdragon from companies like Qualcomm, we can do GPU on board. And if we can do GPUs on board, that opens up all this other deep learning use cases that are really cool. And then one of them that I think is potentially, really important to this conversation is what we call drive-by science. In that thin pipe from Earth to Mars, today they use 200 images of Mars that gets beamed back from Mars from the rovers to decide what to do the next day, where to drive, what science to do, or whatever. Tomorrow, if we use things like Google Show and Tell, and we run it on board, and we get image captions of those images, because text is cheaper and smaller to send across that very thin pipe than images, we can send back a million. Can you remind us
what Show and Tell is real fast?
Yeah, so Show and Tell is basically a convolutional neural network plus an LSTM. It's a head that labels the objects in an image, and there may be many objects. It could be using Inception, which is a model trained on ImageNet, by Google. It could be using VGG from the Visual Geometry Group at Oxford. These various object labeling, models. It's that at the head of the network. And then the other component of it is an LSTM to learn language. It's a word and character-based LSTM to learn the relationships between the language. So not only does it learn the labels that are in the image, the objects, but it learns things like distance. This rock is, further away than this rock. It learns cardinality. There are many rocks. It learns, relationships between objects and rocks and, numbers and things like that. So that's the Show and Tell algorithm. It was made famous by Google, in 2015. And then nowadays, like Scott's talking about with language, they've got all like Show and Tell with attention, what parts of the image are making this label and language happen and coloring it that way and things like that. And so, by the way, what we've done at NASA and partnering, with Google and implementing this algorithm is we have Show and Tell on the rovers in the future. And we've got drive-by science. The rover is telling us what it sees, and it's really, scientifically validated. These labels, we believe in them. And so if we have the rover telling us that, we can get back a lot more science than we're getting back today. The other really cool use case, I'll and then, throw it back to you guys real quick on this, is what we call energy-aware optimal auto navigation. Say that 5 times fast. The idea is like it's an image problem. You look far away and you see out there and it's very sandy. And we know our rover wheels are going to have to drive harder and the motor's going to have to use more energy because sand doesn't catch on the wheels as much. If it's rocky, and I'm oversimplifying this, the wheels are going to catch better. It's going to use a lot less power. So those types of killer applications that are, image, text-based, language-based can, in the future be run on these rovers with GPUs and computings. And that's what gets me kind of excited, because it's an application of all this stuff that we're talking about.
It's also sort of a neat, like we were just talking about, why are we thinking about just text models, image models, blah? Why not have a more cohesive one model for lots of data types? What you're describing is exactly that. It's this rover that's looking at rocks. Maybe it's even taking in sensor data, right? Is that, I don't know. And producing a sentence describing what it's seeing on the surface of Mars.
Totally. And, funny, Scott knows some of this, and I told you the other day too, Dale, but like a lot, that work for B came out of a completely different domain. And it also shows the like cross-domain applicability of all this deep learning and modeling that's not specific to a language, to Mars, to whatever. We originally started working on that in the domain of working with the Defense Department on human trafficking. We were trying to label images basically and caption them and so forth, so that we could find people that were being victim from human trafficking and work with law enforcement and stuff on that. So completely different program and project. And then a couple years later, you got your grab bag of, ooh, this is useful, and it involves Google and language stuff. Oh, I get to talk about this with Scott and Dale. So it's beautiful.
Super neat. All right, let's transition into, we just talked about one really awesome application of, I guess it would be combination image text generation. Let's talk about different applications for these types of really big models. So we talked a little bit about generation. Let's talk about search, something that I'm sure Scott knows a lot, because Google.
Yeah, and so the question is like, where are we using these models in search and whatnot, you mean?
Yeah, like I recently read a blog post that Google integrated BERT into search, that our search, like the search engine, Google it, type search got smarter. Can you tell us a little bit about that?
Yeah, I think what you're seeing here, Dale, is, we've, search have been doing for, decades, obviously. But I think what BERT and these like do is that they have a better representation in a vector for what the meaning of something is, the intent of something. And if you get into BERT, instead of having a single word you're looking at, you can actually look at the meaning behind a sentence, right? And now you can stretch it from a sentence into a paragraph, paragraphs into documents. And we're finding that is prevalent throughout business. So many times in like the Fortune 1000, you have legions of people who are, poring over documents, trying to figure out, or extract data for us to put it into SAP or put it into spreadsheets to understand what's going on. Now you have computers that can start to do that. And so, for years it was, how do I make my business more efficient? Saying, well, maybe I can figure out how to move labor around the world, and maybe I can do, because that's what the internet allowed us to do, and cheaper boxes. And now we're saying, wait a second, can I have one person, basically now have the role of the manager and have the AIs do that for them, right? So that's what so if you look at search, for example, we had thousands of engineers trying to figure out how do you model the intent of these more complex queries. And a lot of stuff that Chris talked about, statistical approaches and feature engineering and everything else, trying to extract it. And BERT comes along and says, well, that maps to this vector. What do you think about this? And then that vector, you can look at pages that have similar vectors and like, my goodness, that's more performant than what we've been doing for 20 years. Because it is able to observe how we searched and then figure out that probabilistic relationship, like we talked about before, like cities and populations, or, man to king, that sort of thing. And now we're using that inside search and actually boosted search results. And so we got excited about that, right? And we had a blog post about it. But that's the general idea, is that we now have techniques that can understand what humans are trying to express in an algebraic form, right? So you can take an expression of Chris or I and turn it to a list of numbers, and it captures, with these neat mathematical relationships, things you can do with it now. And computers love numbers. And so we can now take this and do things that we used to have to, the drudgery of, you can see it in Gmail, right? Gmail does a little bit of autocomplete of a few sentences. It's not a stretch to start thinking about, you start saying, I'd like to write a thank you letter to all the people that came to my party. Boom, you've got 10 letters in your voice, in your handwriting, that you can edit and send. And you're like, you used to have to write those by hand, right? And I think that's the kind of, that's what we're just on the edge of. And we're seeing that a lot in business.
I'm very curious to know what I would say.
Say thank you? Well, it depends on what you said before in your email.
What do I think about this thing I've never heard about? Maybe a model knows.
I think it's going to have something to do with machine learning, and you have some blog series or podcast.
Oh wow! Very smart take on that. So let me go back into what you described before, because it's kind of consistent. So, for example, I might type into Google search, where's the nearest pharmacy? And it sounds like what you're saying is that the way we used to approach this was we'd be like, well, what of the thousands of things that a person could ask for is this? This is a location search or something, right? So it sounds like it used to be a more manual process, but now you throw in something like BERT, a big transformer, and you don't even have to do that kind of mapping, that manual mapping.
Right. And I think Chris talked about this before, which is sort of, it's as though the computer gives you those features automatically, right? So you type in these words, where's the nearest pharmacy, and out comes a string of vectors, but actually it takes into account your context as well. So, for example, Chris talked about, I've got an image, and that's part of it. And then I have an explanation. That's another part, LSTM. And now I can do this auto tagging. Well, I can take what you've been doing on the internet plus the BERT embedding and then figure out what you mean by where's the nearest pharmacy, right? And so that, and the vector.
Yeah, to me,
that's sort of,
the only thing I was going to say is, to me, it was, the trick with this is that before we used to cast a wide net and drag the net through the ocean of possibilities, right? And even Google did a really good job of like coloring that net gold, shrinking it a little bit and making it so that little, I don't know, particular, critters in the ocean couldn't slip through it and, got caught by it. BERT basically takes that net and, does a 3D scan of Dale, and then make sure that only the things that we care about, for Dale in those little, I don't know, you can't even imagine them, but rectangles, triangles, stars, and whatever, those don't sink, those get caught in our net, and that's the net that we're dragging, with BERT, when we do that for semantic search with Google and things like that. It fundamentally re-architects and changes the net, for that.
Very neat. So, okay, this next question, also on search, I want to ask to you, Chris, because we talked about this the other day. All you've described are very great for querying documents on the web that have text, but increasingly, there are videos, there are live streams, there's Google Maps data. How can we use a similar technology to expand into all of the non-text data types on the web?
Yeah, so for me, I spent 10 years basically hand writing with a big team of people parsers, which evolved into this thing called Tika, which is what I call the digital babble fish. It was and again, it's statistics to black wizardry.
So what is Tika?
Yeah, Tika is a library. If you're familiar with the Hitchhiker's Guide to the Galaxy, the idea with the babble fish is you put the babble fish to your ear and you can understand any language. And so we call Tika the digital babble fish. You give Tika any file, it'll spit out what the file format is in one of the 1,000+ IANA media types of the internet, anything not just text but application, image, audio. It'll tell you what type that is, and then we've curated a library of basically all the parsers that are free and open source to basically extract text, metadata, and language information out of any of those file formats. And for years we did this statistically and by hand and writing parsers, and fundamentally how the game is getting changed by deep learning and GPT and BERT and all of these things today, by inception models, by deep speech, LSTMs, and things like that, is that now that we have models of the brain to see, think, hear, generate, imagine, all of those things, the possibilities for feature generation, it doesn't matter what file format you have. We can automatically detect it with high accuracy. We can get back text, metadata, and whatever. And the challenge for us for the last 10 years, it was a pain in the ass to write code to do that, because they're very brittle code over the years to do it. Tomorrow, it's not going to be with these techniques. With these techniques, because we're going to model them after humans and the brain, it's not about the code you're writing. It's about the amount of data and training that you give to them, and your ability to model, the outputs, which in this case are basically text, metadata, features, and things like that. So at the end of the day, given your comment earlier, Dale, that the internet is an infinite source of labels, but it's, unstructured and things like that. What if tomorrow, it's like the Morpheus. What if I told you, red pill, blue pill, that tomorrow, the blue pill or whatever is going to be that you don't need to do that anymore. That infinite, and this is what Andrew Yang's talking about when he says, data is the new oil, and that we refine it, and things like that, and all the work with data for humanity. What they're talking about there is that there is an infinite source of data and labels, and it's just the crude. You don't want the crude. I want my $1.92, whatever unleaded, that's been refined, and the refining process was really hard before, and tomorrow with machine learning, deep learning, and all this stuff, it's going to be really easy. So
That's well said. And I think, Dale, you're getting it before is that if you think of words as sequences, right? And well, so are pixels. So is voice. It's sequences of frequencies. And so now we're starting to see researchers saying, well, if I can do it for byte pairs for text, well, why not an image? Why not speech? Why not video? But if you think of video, I mean, the sheer size you'll need to do something at GPT-3 scale for video is quite large. And the point is, you're now approaching things with you get into these transit connections, and you can imagine spending tens of millions to build these models. But what if you could feed a model like GPT style of a BERT model all of YouTube?
So this is a really interesting topic. So at the beginning of this live stream, we talked about how one of the things that makes these new language models like GPT-3 and BERT so powerful is their ability to learn from untrained data. So you take a document, you spit out, you block out some words, and you say to the model, your task is to predict the blocked out words. No human labeling required. So now you're suggesting, well, maybe we do the same thing for other data types. That's what it sounds like.
Right. So imagine this in images. You start blocking out chunks of images and say, imagine what's in the missing part of the image, right? And you can imagine that for a set of images, and now it gets pretty good at auto-completing an image. And then you make it larger and larger and larger. It says, there's a person standing here. What would that look like if it imagines it, right? So why not in video? You're doing tweening in video. So imagine you do a couple frames and it sort of shows you the people moving. Like, that's kind of freaky. But no, it's mathematically very similar to just guessing what Mad lives, just in a higher dimension. Right. And so if these models scale that well, that could be extraordinary. Right. So now we have these tools that can generate video directly and augment our video as a tool that someone in 7th grade can use.
Do you think that building,
sort of
I was just saying, do you think that building this type of model for video and images, is it more difficult than text? Is it more data and computationally intense?
I think they're all difficult, but I think if you look at it in terms of the mathematics and the idea that there's sequences and imagining sequences, but in a higher dimension, right? That's video, right? Because video is images over time. And instead of having just a 1D of words, it's 2D, maybe 3D if you got red, green, blue, but it's just a tensor. It's a high dimensional vector. And so the mathematics works, the scale is extraordinary. And so, I think we're going to learn and get into that, but I think that's sort of captured the venture community imagination, thinking that if this scales, if this works, what if you could feed all of network television into a model? What if you could feed all of the recorded human voices and it auto completes like his Mad Lib's voice? Now you've got the ability to represent, and you could have 10 meetings in parallel and be there.
The other props I'm going to throw as a fanboy of Google here, this lowly NASA scientist, is that the framework approach to doing this that Google took, and this is going to relate back to the energy question, is it's not just taking that model training and throwing it onto GPUs and computing. What they did is they abstracted out through the tensor the ability to deploy those and to train, run them, and compute over them over time, which is one of the beauties of the framework approach to doing this with TensorFlow. Is like your deployment, your whole model, your training, your predictions, your ability to kind of do all the data cleaning, all of that stuff is a lazy graph that is only executed, through a placement, on devices or whatever that happens later. And so you do have full control, of where that actually executes, trains, runs, makes inferences and stuff like that. And that's the power, is that before it's not like, and by the way, like the community doing this is, it's the people we're familiar with. You go get a PhD, it's, hey, we all wrote our research code that only ran on our laptop on that specific, amount of memory, and usually only 3 out of 7 times, because that's research code. Most of the other times it, failed in memory, malloc, bad memory, screwed it up. But those 3 times it ran, But the Google TensorFlow approach is that they took the research people and they said, okay, this is great, research people, but we actually have DevOps deployment. It's got to scale, it's got to run, and we got to be able to configure that. And so that's another kind of key thing. I want to give you guys credit. That's been a key thing for me at least.
Yeah, you're welcome.
You're welcome. Yeah.
Is this sort of language stuff something that is the stuff we talk about today covered at all in your new book on TensorFlow, Chris?
Yeah, basically, the way Scott describes it, I'm going to steal his words because I like it, is, it teaches you it's a progressive way of teaching you how computers have learned to think, hear, see, listen, and things like that. But before you get to that, it walks you through, and this is the thing I like about the book. Everybody jumps straight to deep learning today, but statistics matter. Explainable models matter. And, so the book takes you through basically explainable models, regression, classification, hidden Markov models, clustering, unsupervised. You still need all those techniques. And so we used to say 5 years ago that, oh, deep learning was black boxes. I've been dissing deep learning this whole Twitch stream. It's not all black boxes. We're getting better at explaining it. Big $100 million government investments and big investments at the tech companies like Google and Facebook are getting better at explaining deep learning, feature engineering, and we know more neural architecture search. We know more about that. So I sorry, neural architecture community, I'm just messing with you. You're not, totally in the dark today. However, why not? Don't throw statistics out. Start with basically explainable models, because you never know when you need an explainable model to explain a part of the architecture for your black box, deep learning thing. And so the book walks you through the whole thing with that. It starts out with explainability, and then it gets into the dark arts and horcruxes of, biological models.
That's awesome. I will definitely pre-order my copy. And with that, I think you left people with a really great starting point, and we're just about out of time. So thanks so much for joining us. I had a lot of fun in this talk.
Well, thanks, Dale. Thanks, Chris. It was great hanging out with you all today, chatting about embeddings and BERT and GPT-3. And it's one of the most exciting things I've seen in computer science in my career. It's amazing.
Yep. And thanks to both of you. And everyone join us for our new thing. It's called the TensorFlow Bunch, and then we'll point at each other,
Yeah.
The TensorFlow.
And cue the music.
Like this, like Chris.